All right, so properties of, that's the typo. That's supposed to say definite integrals with a capital D, not indefinite integrals. Um, sorry. Yeah, it recurs. It happens all throughout this lecture, it looks like. Okay, so properties of definite integrals. So at the beginning, when we started to talk about Riemann sums, we talked about the definite integral gives you the area quote area or quote under, any way you want to quote it, kind of just a certain level of uncertainty there. And it has to do with the fact that that gives you the signed area here. For this example here, we're looking at sine, but this time instead of being symmetrical around the y-axis, never mind, you see the picture. So this area is going to be counted as positive area since it's above the x-axis, and this area is going to be counted as negative area since it's below the x-axis. And just to explain why that is, let's think about how these areas are calculated. Well, they're calculated by taking an interval and defining a rectangle, a very, very, very thin rectangle, because you've taken an infinitely thin step size, so in other words, an infinite number of slices over this interval. But to see it, you can draw it a little bit bigger. And so what's the area of this rectangle going to be given by? Well, our base is delta x. That's a step size. That's a positive value. But this, the output, the height of this rectangle is actually going to be a negative number. So the area of this rectangle is going to be the positive delta x base times height. Well, the height is going to be f of x star there, our x star, and that is going to be a negative number. So positive times negative is actually going to give us a negative area for the rectangle. So rectangles that are above the x-axis are going to have positive area, and rectangles below the x-axis are going to have negative area. And so sure enough, if you were to do this integral, we don't yet know how to do that, but you would get 0 because the positive area and the negative area, since they're symmetric over the interval from 0 to pi here, this red one, is equal to the area. Now here I'm using the word area to represent actual physical area, so areas are positive value. They're both the same, and since they're symmetrical, the negative one's the same as the positive one, they're going to sum to 0. Okay, so here's the meat and potatoes of this lecture, or this particular video. And again, apologies here. It's not indefinite, it's definite integrals. The area of a single slice is 0. Okay, well, what does that look like? Okay, so here, notice the key to this one is, the key idea here is that your limits of integration are the same. So what would that look like in a picture? Okay, so here's our function. And if I just start my interval and end my interval at a, then my rectangle is infinitely thin. It's just a slice, a vertical line, if you will. And sure enough, that should have area 0. Another way to think of it is your step size is equal to 0 on this one because the interval has length 0. So yeah, kind of, it's not a silly example, but kind of it's an example. All right, the next one, let's see. The next one is what? The next one is swapping limits of integration. You swap signs. So what does this look like? Well, for example, if we had from 0 to 2 of some function, say it was x squared, but for some reason, our integral is going to be easier to deal with if we put the 2 on the bottom and the 0 on the top. Actually, let me start that over. More often than not, this one's applied when you have an integral where the limits are in the wrong order. So say I had 2 to 0. 2 is less than 0, so we're used to having that on the left, so that should be on the top usually. So if we had 2 to 0, well, then of some function, you can just switch the order of the limits and you get a negative out in front of your integral. You can play that regardless of which order the limits of integration are. Maybe the problem becomes a lot easier if you do the limits of integration in the opposite order, and so you want to switch it and you just pop a negative sign or switch the sign that's out in front of the integral. Integrals are nice. You can split them up over sums. So if you got two functions, x squared and 3x here, then you can split up your integrals and just deal with an integral of x squared and an integral of 3x, just like indefinite integrals. We saw that as well. And then just like indefinite integrals, you can factor out. And again, I'm using the word factor improperly here, but it's an okay intuition that if you have a constant number multiplied by a function, you can just pop it out in front of that integral, the k number there. Okay, so here's another important thing that we actually use when we're trying to find areas. And so it's called the additivity of the integral over a continuous interval. So basically what this says is you can break up and add the results of consecutive intervals. So you've got your integral going from a to b. Okay, so you've got some function a to b. And our function looks something like this for that. And maybe the calculation gets a lot easier if I could just go ahead and add a c value in here. There's our c. Notice that c is between a and b here. A is less than c is less than b. Then you can split your integral up into a first integral where you calculate this first area from a to c, and then a second integral where you calculate the area from c to b, and you're looking at those limits of integration there. There's a very, very nice applet in the reading assignment that I really encourage you to take a look at, demonstrating this. Okay, so let's do a few examples. So it says to expand using properties, using our indefinite integral properties. Okay, that's going to bother me. I should change that to definite. Well, you just cross out the in. Okay, so what can we do here? Well, I can split it up over this. So let's do that first. So we'll say that this is equal to the integral from -2 to 1 of 3x squared dx, still with respect to x, plus integral from -2 to 1 of 2x, still with respect to x, so dx, plus integral from -2 to 1 of 2 dx. So here we split it over the sums. Sums and differences are the same thing, so I'm just going to say sums. And you know what else we could do? We could pop those numbers out front. I could pop that constant 3 out in front, so get 3 times the integral from -1 to 2 of x squared, and then we know how to do that with our power rule. Plus pop that 2 out in front, -2 to 1 x dx, plus you could factor out that 2, and again, it's not factoring it out, but it's what it looks like, so it's an okay intuition, and just be left with the integral of 1 dx. And here again, I'm putting quotes because you're not actually factoring it out. It's factor through. But again, intuition, constants. And we've expanded it as far as we can using the properties that we have. So for our next example, let's see if we can figure out this. Just given a problem, let's see what we can do. From 0 to 8, we know the area is 10. And from 0 to 5, we know the area is 5, and we're asked to find the area from 5 to 8. Okay, so let's draw this in a picture to help us think about this problem. Okay, so our x-axis there is we have from 0 to 8, and I've got some kind of a function that does something like that. I don't know. It doesn't matter. It's not going to be accurate. Okay, so we know that this whole area in here, this whole black area from 0 to 8 from this first integral has an area equal to 10. But the second integral tells us that from 0 to 5, we have this much area. We have an area of 5. And the question asks us to figure out the area from over this interval from 5 to 8. So we want to know this area here. We don't know this area. But here we're exploiting the idea that so-called additivity. If you have a continuous set of intervals, you can add together chunks of area. So the blue area plus the red area should give me the black area. Area plus my red area equals the black area. Well, so what is the blue area? Well, the blue area is the integral from 0 to 5 of our function f of x dx, plus the red area is given by the integral from 5 to 8 of f of x dx, and that's equal to our overall area, 0 to 8, f of x dx. Now we can fill in these values. We know that the black integral is 10, the blue integral is 5, and the red integral is what we're trying to find. So plus 5, 8, f of x dx. Subtract 5 on both sides, and we have isolated our problem child, our integral. And so we get as a conclusion that the integral from 5 to 8 of f of x dx is equal to 10 minus 5 is equal to 5. And I wanted to go through that symbolically and show that, because if you could figure that out just by looking at it, that's great too. But I think drawing out the picture and really thinking it through is helpful. Okay, so we've just got one more example here, and so we'll do that one. And again, I'm not giving you any rules of how to work with definite integrals, but rather just saying use geometry to evaluate the following integrals. Okay, so we got to draw a picture. Okay, so what does this one look like? This looks like, well, you've got a height of 3 over the interval from 1 to 4. Okay, so 1, 2, 3, 2, 3, 4. So what's this function? Well, the graph of the function is going to be just a horizontal line, because y equals 3, f of x equals 3 there would be, this is f of x or y equals 3, and this line is. Okay, so what's this area going to be? That's just a rectangle. And so geometry lets me take the length times the width. The height is 3, and the overall base is 4 minus 1 is 3. So 3 times 3 gives me an area of 9. Geometry, and we sorted it out. So let's do a different one. Here I'm going to give ourselves a little bit more room, because here we're taking a look from, and I want reasonable to be reasonably accurate here. Okay, so give ourselves a nice big thing. This example B goes from 3 to 4 to 5. I'm kind of playing fast and loose with because we don't care about to the left of 3. Okay, so now 2x is a pretty steep line. It goes through 0, 0, and see, our function is f of x equals 2x. So the point for 3 would be f of 3 equals 2 times 3 is 6. Okay, so we go up here. Maybe that looks like height 6, fairly reasonably. F of 5 equals 2 times 5 gives us 10. So if that's 6, then maybe this is 10, and we got 5, 10 right up there. And this is our line. Is it perfect? No, but it's a good enough picture. And so we need to figure out this area here. And so the game here is to say, well, use geometry and break it up into pieces that are relatively easy to calculate. And so I'm going to propose that we just do the area underneath this as kind of a square. And this is a square. So the area here is equal to, this side is 2, and then the height is 0 to 6. So the area is equal to 2 times 6 gives me 12 for that square, or rectangle rather. And now above it, we have a triangle. And geometry formulas for triangle, area is equal to 1/2 the base times the height. Well, I can figure out both of these things. The base is, just like my rectangle, going to be 2, and the height is going to relate to 6 to 10, so that's 10 minus 6 gives me a height of 4. And so the area for this thing is going to be, area is equal to 1/2 times 2 times 4, so those will cancel out, and I'll be left with 4. So the area in here is 4. And so the total area, what that integral gives us, and since it's above the x-axis, it's all positive. If you had to do this with one that had below the x-axis, just remember to have them be negative, unless they're asking for the physical area, not the total signed area. But total area is going to be 12 plus 4 is equal to 16. So the answer to our integral is equal to 16 using a little bit of geometry. And that's the end here.